So hello everyone. So today in this class we will be discussing week 3 of the course unit operation of particulate matter, and in that specifically we will be looking at yes. So let me come to the screen. I hope my screen is visible. Let me see. Yes, I am presenting. Yes. So in this particular lecture, week 3 of course unit operations of unit operation of particulate relate matter. Okay, in this week was more inclined towards the working modeling and the application of fluidized bed. So this was about fluidization or fluidized beds. Okay, so these are some key discussions. So this in this lecture we will be discussing some of the questions that will be helpful for solving the week assignment, and the questions will be directly or indirectly related to the questions that are being asked in the weekly assignments. And so this this will be helpful for you in terms of getting thorough understanding of the concepts, and also the 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 clearing of the doubts whatsoever you have, apart from what has been already told in the lecture. So the first question that I will be posting is about the fluidized bed, and this question is this one. You see, uh, in a fluidized bed, bed height increases along with the pressure drop. Bed height increases at the constant pressure drop. Pressure drop increases at a constant bed height, and the pressure drop and the bed height do not change. So which of the following is correct answer? So if you look at this, you just try to solve it. Meanwhile, I will be telling you. You try to solve it based on whatever concept has been taught throughout the week, and we will get in touch to get the answer of the same. So solve it. So look at the question and read each option carefully. In the lectures, it has been taught through the theory also, conceptually, and as well as through the equations also. This will be clear that in what situation there is a constant pressure drop, or that is responsible for the increase in height, and vice versa. So, so the answer for the question at hand is bed height increases. Bed height increases. Bed height increases. Yes, bed height increases at constant pressure drop. Bed height increases at constant pressure drop. This could be also clear from the graph that you already had during uh, the explanation of the fluidization, and there you came to know about, like, this this you see, uh, the curve that was there is this one, where you came to know that where you came to know that fluidization characteristics fundamentals, and there you came to know that this is bed pressure, which is delta p time, and here the gas velocity. Okay, this is UMF. At the UMF, which is the minimum fluidization velocity, we had the pressure drop to be increasing with your gas velocity, and then it comes to almost constant pressure drop. So so what is actually happening as you are putting the gas, as you are increasing the gas velocity from the bottom, the pressure drop is increasing. Okay, even the pressure drop is constant. Even the pressure drop is constant. uh, the 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 bed is fluidized, so there will be increment in the height. So bed height increases at the constant pressure drop. So the answer is, in fluidized bed height increases with the constant pressure drop. So bed height increases with the constant pressure drop is the correct answer. So the second question that is that you need to solve is, at minimum fluidization condition, which of the following is true? So I will be putting some options. At minimum fluidization condition, which of the following is true? At minimum fluidization condition, which of the following is true? You see this particle starts moving freely in the bed. Particle starts leaving its place in the bed. Both of the above and none of the above. So which of the following is correct? If you see which of the following is correct, at minimum fluidization condition, particle starts moving freely in the bed. Okay, particle starts leaving its place in the bed. This is clear from this particular diagram also, like this one. This also relates the same conceptual clarity. Uh, like uh, if you see, okay, so particle start leaving its place in the bed. Somebody is there. Let's see. Okay, yes. So at the minimum fluidization condition. Okay. So you think about this, and so obviously when this fluidization is happening, admit. Okay. So this question, like second one, is at minimum fluidization condition, particle starts moving freely in the bed. Particle start leaving its place in the bed, both of the above, none of the above. So obviously when the minimum fluidization condition will be achieved, for example, this usually happens at this particular s- location, as explained in the first lecture of the week, of the third week, uh, where you came to know that this this is the situation where before which your pressure drop across the bed was is linear with the velocity of the gas that you are putting from the bottom. But just after that, the motion among between the particle, or particles start moving zigzag or irregularly because of the gas. Like this is the bed, and initially this bed was packed because whatever drag was felt by these particles because of the air gas velocity from the bottom was not having that much influence, uh, uh, that it will move. But when you have reached the velocity which is UMF, which is the minimum fluidization velocity, the particles started moving. So the definition of the minimum fluidization velocity itself says that the particles start leaving its place in the bed. So the option B is the correct answer. Particle starts leaving its place. So they will be localizing. So I will be explaining it through the definition of minimum fluidization condition also, place in the bed. So if you actually see this condition for the minimum fluidization, and then the formula for the minimum fluidization velocity, from there you came to know that the porosity, not the porosity but the epsilon terms come up. That epsilon term is actually taking care of the voidage, and that voidage is nothing but the that came up because there has been some motion imparted within that packed bed because of this gas velocity. So this this particular uh, explanation was given in this slide that was there in the first one. I will be putting that first, and then it will be easy for me to explain. Here you see this. You was initially the bed was packed, and you was the increment in the gas velocity was taking place. So gradually you see that at the end there has been pneumatic transport that is having clearly different application. But this particular uh, the third and the fourth and the fifth, here you actually see that starting from the second one, the relative motion started between the particle, and this motion is actually coming up and leading to the void, and that again happens when the fluidization start, means the lifting of the particle starts, and this this velocity is explained in terms of fluidization, minimum fluidization velocity. uh, and this the first question that I was talking about is uh, is also explained in terms of this only. Like you see this minimum fluidization velocity, before that packed bed was there, but after that it became fluidized, mean there is some void coming up and particles are not that much packed, so the bed height increases. That is nothing but the first question. The in the fluidized bed, bed height increases at a constant pressure drop. So it doesn't increases always with the pressure drop, but it increases at the constant pressure drop. You see here it is clear that bed height and the incipient fluidizing velocity is there. So this fluidizing velocity, which is the velocity of the gas and the height. So using this correlation and the one, you will be able to see that when the pressure drop is constant, the velocity is the bed height is increasing. So the first question that I told could be explained through the through this diagram also, that the 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 bed height is increasing at the constant pressure drop, but height was constant when the pressure drop was increasing linearly with the velocity. So that is all for this these two questions. First one was in fluidized bed. It has been actually about the bed height and the pressure drop condition, and the another was one was the minimum fluidization condition. Like this is the incipient fluidization condition. That is the thing with the minimum fluidization condition, where after which the lifting up of the particles starts. And now the another question that I want to pose is about the Galileo number. And as you know, this Galileo number is involving the gradient of density and gravity also to some extent. So how you will be going to look at this uh, in terms of the fluidization. So with increase in Galileo number is, so what will happen when you are increasing the Galileo number? Ratio of the terminal settling velocity and the minimum fluidization velocity increases. Ratio of the terminal settling velocity and minimum fluidization velocity decreases. Ratio of the terminal settling velocity and the minimum fluidization velocity remains constant, and none of the above. So you actually look at this and try to use the concept that has been taught in the week, and meanwhile I will discuss with you about the same question. So I will be giving 2 minutes around, just solve it. So I hope, who is there? Nandita Yadav is there. So you solve it and then let me know. In the comments also you can just write which option is correct, or whatever you feel like. Even you don't know exactly, you can try, give based on your intuition what it says, and so on. So this question is a bit straightforward. In the lectures, this has been explained when the discussion about the Galileo number and the calculation of the Galileo number to calculate the Reynolds number at MF, minimum fluidization. This was being discussed. There, this came that the competition between the terminal velocity and the minimum fluidization velocity will be the one which will decide the extent of the fluidization, or like the fluidization in the in the regime of particulate fluidization or in the bubbly fluidization. So that particular discussion will be necessary in order to solve the question. So just give a try, then this will be good for you to actually feel the problem. So as the Galileo number is being increased, what is happening to the ratio of terminal settling velocity and minimum fluidization velocity? So this is an important discussion, and if you look at the explanation that has been given in the lecture, there you have been told that this graph was there. I will be posting this graph, and then things will be easy. So this, though this is a bit not clear, but yeah, this will help. So you see this one here, this has been told that the ratio of this uh, this has been told that the ratio of the Reynolds number at the terminal settling velocity or terminal falling velocity, okay, to Reynolds number at minimum fluidization velocity against the Galileo number it has been plotted, and from this plot you see this u0 to umf. U0 is the terminal settling velocity, to umf has been plotted against the Galileo number with EMF void at the minimum fluidization as a parameter, and you see this graph is decreasing with the Galileo number. So from here you come to know that this ratio of the terminal velocity, settling velocity and the minimum fluidization velocity decreases with the Galileo number. So option B is the correct answer. B is correct answer. And why this has been used during the course, you have got to know from where this graph came and how this discussion came into existence. And this was actually first like when you was calculating the minimum fluidization velocity in terms of terminal settling velocity, then there you encountered this particular curve that was relating them. And this obviously this has been calculated experimentally, but this Galileo number explains like whatever Reynolds number at the minimum fluidization condition and terminal falling condition, we obtain the ratio of this, and we can calculate and we can allot this ratio over this graph, and through this graph this based on the Galileo number, this ratio can be predicted for given void at minimum fluidization. So option B is the correct answer for the given question. So this is let me see. Somebody is there. No. So this is all for this. When this discussion was happening, maybe you may have encountered lots of things, and then this uh, the ratio. Therefore, the ratio of Reynolds number at the terminal falling velocity to minimum fluidization can be related with the Galileo number using these curves. So here you can see that when the Galileo number is very small, at that point the ratio of the Reynolds number at a terminal falling velocity will be higher in comparison to the Galileo number in a higher Galileo number. So you see this. So it is clear, and now we will be moving towards some other question. Let's see. This question is about. This is fourth question we will be discussing, and this question is about irregular particles. So let's begin with the question. So this question says more irregular particles means increasing bed voidage, decreases bed voidage. Both are possible. None of the above is correct. So which of the following is correct for the same? If irregular particles are there. So for irregular particles, which of the following is correct? Hmm. So irregular particle, which of the following is correct? And you see increasing bed voidage, decreasing bed voidage, both are possible, and none of the above is possible. So if the particles are irregular, then there is chance of decreasing bed voidage. That is the correct answer. B option is correct. So obviously, if the spherical particles are there, then there will be some void is coming up. But if the irregular particles are there, then it has been proven that experimentally that the decrease in bed voidage has been observed. So now the next question, which is like about the same, somewhat gas and the liquid velocity related problem, and this problem is directly taken from the slides. So hope you understand this. Is this says uniform expansion of the bed is not achieved in which of the following the uniform expansion of the bed is not achieved? Low gas velocity, low liquid velocity, high gas velocity, high liquid velocity. So which of bed is not a bed? Like uh, this you think which could be the correct answer? So that has been explained in the lecture through 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 some graph, and this explained that in the case of gas and the liquid, like where the discussion of the bubbly flow, and then this slug and everything has been discussed there, you will come to know. For the liquid fluidization, you know, if the liquid is flown from the bottom, the, that is the liquid fluidization, and this, in that case, you know that this particular thing is correct. And this explains the uniform expansion of the bed is not achieved in uh, low gas velocity, in high gas velocity, in low gas velocity, in low liquid velocity, high gas velocity, and the high liquid velocity. So think about this. And meanwhile, I will be looking at some of the other problems, and so related materials I will be telling you. And this, so this bubbly fluidization because of the gas. Sometimes gas and liquid both is used, and based on that, the condition for fluidization and the characteristic of the fluidization can be predicted. And obviously this state of the fluidization, and obviously this Froude number and the factor, and based on which you decide that which regime the fluidization is, whether it is a bubbly fluidization or whether it is a uh, whether it is a bubbly fluidization, or whether it is a normal fluidization. So which is particulate fluidization. So I will be putting up some of the important, just 1 minute. Yes, just 1 minute. Hello. वो वो दीदी हॉट एयर, प्रतु भैया जहाँ सामान रखते हैं ना अपना, हॉट एयर ओवन, उसके सामने वाला जो टेबल है और वो बेंच है, उसके ऊपर में रखा होगा, जहाँ पे पैराफिन वगैरह लिखते हैं। हमारा क्लास चल रहा है, हम बात करेंगे। ठीक, ठीक। यस, सो या सॉरी, so this is all about the we were where we were. Yes, this question. So uniform expansion of the bed is not achieved in which of the following? So you have to actually look at each in detail, then only you will be able to. So each figure, like what was and how the things were changing when you was increasing the flow rate from the bottom for the liquid or for the gas. So then you will be able to tell that what is actually happening. So this is case of particulate fluidization. And aggressive aggressive aggregative fluidization is also another aspect. So about that also I will be telling you, and then we will compare this. Yes. Okay, so this particular thing is like uniform expansion in the bed is not achieved. So these are not uniform expansion, you see. This one is anyway uniform expansion, but this is not. This one is uniform, and this is not uniform. This is also uh, uniform, but if it is very large, then there has been some of the problem, like you had seen that there has been formation of the channels, there has been formation of bubbles which were non-uniform. Direct lifting of entire bed has been observed, like bed is getting lifted. Uh, instead of getting fluidized. So this particulate fluidization is the one which is very good. So in this case, at the high gas flow rate, or if you see this at the high gas velocity, mostly you don't get the high gas velocity. This is gas velocity. If the gas velocity is very high, mostly you don't get your bed to be uniform. So the option C is a correct answer. C is correct answer. Okay, so that's the I think fifth question. Now the sixth question I will be posing up, and then we will be going for some other questions. So the sixth question is so the sixth question is the sixth question is for given terminal settling velocity, operating fluid velocity is if the settling velocity is given, the operating fluid velocity is so between that given terminal velocity and the operating fluid velocity, the increase in the bed y dash, decrease in the bed yz, both are possible, none of the above. So so for the given terminal settling velocity, operating fluid velocity, increase in the bed, decrease in the bed, and then so this operating velocity, what will happen to this? So as far as I remember, if you remember the formula that was actually relating this uh, voidage, terminal velocity, and the uh, operating velocity, there you came to know that the value of n is the thing that was deciding what is actually happening to the system. Okay, and so this value of n is the one that actually tells you what will be going to happen. And if you remember this, the just void thing, and this uh, so this u by equals to e to the power n. So in this, as far as this given terminal settling velocity, operating velocity is, so if the terminal settling velocity is given, and this is what this usually is in fraction. Usually this is a fraction, and though this has been used for different condition like Richardson Janke equation. There they have showed that the corresponding velocity at the infinite dilution and the impetus velocity ratio, and this so that is nothing but the operating velocity, which is u zero, and ut is the terminal velocity, and this this when you relate, you come to know that the increase with the increase in the bed voltage. So if bed voltage is increasing, if the terminal velocity is fixed, then operating velocity will obviously increase as the voltage will be increasing. So increase with the increase in the bed voltage. So that is the sixth question, and you reply sometimes if you feel like, and then give reply in the comment, and also try to solve these questions. These videos will be recorded, so these videos will be anyway available afterwards also, so you can go to this. And so for a given terminal velocity, operating fluid velocity increases. So I will ask one question in this particular upper question. So which of the following this one the which of the following do you think that will be used for conveying uh, solid particle, and why conveying solid particle through fluidization will be much helpful as compared to the any other transportation methodology that is being used. So you think about these questions, question and reply in the comment if you get to know. I will be joining in a minute. Yes. So I hope I hope you have thought about this. Like this, this is the last one. You see, when the the gas is having that much velocity that the entire solid particles are got lifted from the distributor. None of the solid particles are near distributor, and gas is threatening rain is there. So this can be used for the pneumatic transportation, and this is none of the solid particles are much striking the walls, so there will be no frictional loss associated. So this is the most convenient methodology for the conveying solid particles through pneumatic transportation. Okay, so now we will be moving for the next problem, uh, and the next problem is the about the value of n, and this is the one factor that came up, and let's see. So try to solve it. The value of n is higher for small particle size, large particle size, irregular particle, none of the above. So which of the following is correct? The value of n is more for large particle size, small particle size, irregular particle size, particle, and none of the above. The value of n is more for. So through the curve, as far as I remember, mm, and this will be very helpful for you. And this this n that was there, this n, if you see this n is high for what? Think about this. So if you remember, this was discussed in the lecture. This n will be higher for large particle size. Okay, so this is the large particle size is the correct answer for the given problem. Now we will be solving some of the numericals. So the question 8 now is that I am going to discuss. So first, I will be writing the question is calculate the minimum fluidization. So rather I just pose the question so that you actually go to the question and we will be solving it. That will be a bit faster one method. Just just go through this question, and then we will be going for the solution of the same. And this is it. Calculate the minimum velocity at which spherical particle of the density 1500 kg per meter cube and the diameter of 1.2 millimeter will be fluidized by the water in a tube of diameter 8. This is the diameter of the fluidized bed. On the assumption that you are actually assuming that the situation is laminar, so Karman-Gosni is applicable, and the voidage is 0.45. Also, the correction factor to account effective effect of the wall is 1.1. So FA is also given. So just try to solve this question, and meanwhile I will be telling you the solution for the same. And So we will be solving three numerical problems now, and then we will be solving some more theoretical problem. And when then afterwards we will see if time remains, we will be solving some more questions on sphericity and all. So sphericity was also introduced somewhere when the irregular particles has been considered. For example, cylinder, for cylinder one numerical is also explained where the sphericity has been calculated to be 0.82 or something. And through the graph you came to know that the what is the meaning of fluidization and the designing of the fluidized bed. Yes. So calculate the minimum velocity as this spherical particle of density 1500 kg per meter cube and the diameter 1.2 mm will be fluidized by water in a tube of diameter 8 mm on the assumption that the Karman-Kozny is applicable. Voidage is 0.45 and the correction factor is account effect of wall is 1.1. So you please see. Now we are going to solve this. Let me change the color. Yes. So here the density of solid is given. This is density of solid and this is equals to 1500 kg per meter cube. Also, you are given with the density of the liquid. So here water has been given. So density of the liquid is 1000 kg per meter cube. Viscosity of the water, you know, and diameter is 0.0012 meter. This diameter is what? 1.2 mm. Okay, and the voided is given as 0.45. Okay, so the correction factor to account effect of wall equals to correction factor to account effect of wall equals to 1.1. Okay, so this is the one thing. So Karman-Kozny equation says, if you remember the Karman-Kozny equation, as here the situation of laminar, so we consider situation Karman-Kozny. So this Karman-Kozny equation says UMF equals to 0.0055 epsilon cube divided by 1 minus epsilon and then d square rho s minus rho g divided by mu. Okay. So what is this? Substituting all the values UMF equals to 0.0064 meter per second and considering wall effect UMF equals to 0.0071. Why? Because as when you consider the wall effect, you will be actually using this 0.45, this 1.1 to be the one factor, and get multiplied, and then 0.0064 multiplied by 1.1 gives 0.0071, and this all the values has been given. The void, so this factor is completely known. D, you know, density of the solid in the liquid, you know, gravity, you know, and viscosity of the liquid, you know. So everything is known and the UMF has been calculated. So the next problem that we are going to solve is the the one that is here, that is related to the above question number 8 only, is find the minimum fluidization velocity considering Ergun equation. So there you have considered the Korsnick Harman equation. Now it has been told that you just consider the Ergun equation to tell the uh, this minimum fluidization velocity. So as you remember in the lecture, you have uh, calculated this using when you consider the Ergun equation and you solve for this, then uh, the Galileo number comes into the picture. And this Galileo number, if all the data you take from the part one, so I will be actually taking the data first from the part one. Okay, so let me see. This is, so let me take it from here. Yes, now it is okay. Okay. So this data is given. Okay, so let's get the data from the question itself. And now uh, using the Galileo number, that is dq, density times density of the solid minus density of the liquid times gravity, acceleration due to gravity, divided by mu square. And when you put all the values over here, the diameter was how much? 0.0012, 0012 whole cube, density, you know, 1000, okay, 1500 minus 1000, okay, 9.8 divided by mu square, which is 0.001 square, you get 8475.8 is the Galileo number. So now using the formula for the minimum fluidized condition Reynolds number, so Reynolds number at minimum fluidized condition for the from the Ergun equation, 23.6 m1 plus 9.39 uh, multiplied by to the minus 5 Galileo number. Okay, and this is minus 1, and you when you solve it, you are going to get 8.503. So through REMF, you know, Reynolds number, you know, So through that you can calculate UMF as rho u rho u d by mu can be used density times velocity times diameter divided by viscosity will give the Reynolds number. So you can be calculated using that, and this comes out to be 0.0067 meter per second. Okay, this is the UMF. And when you consider the wall effect, if wall effect is considered, wall effect is considered, so the UMF is 0.00737 meter per second. Okay, so you now you see how the value changes with the positive carbon and the argon equation. So that is all about that question. And then when you actually want me to explain you about that, how that all happens and how that equation, the derivation for the same equation is done, let me just tell you about the, just look at this, where the discussion came up. So as far as you remember, you see this one. This one I was telling. This was the, before that you learned about the Kazhnikar law. So it is necessary to use one of the Bohr general equation for the pressure gradient in the bed, which is Argan equation. When the flow regime at the point of incipient fluidization is outside the range over which Karman Kozny is available, you have to go for this. So this is the Argan equation, and when you employed this Argan equation, like said in the question number 9, you had this one. And then further when you derived the expressions, you got this RE expression to be this in terms of Galileo number. And you know this UMF equals to mu by dP RE MF, yes, d rho, and through that you have calculated the density. Okay, so that was it about the question. So the effect of wall also you considered, and you got that 0.00737 is the correct answer for the given problem. So that's it for the question. And now still we are having plenty of time, and we will be solving some more numericals. And so so this is the all about question number 9. Let's take question number 10, uh, which is again based on this fluidization and terminal velocity dependent question. And I will be giving you 2 minutes to solve this question, and then we will discuss the same. Okay, so let's see this problem. Yes, so you solve this. Derive the relationship for ratio of the terminal falling velocity of a particle to the minimum fluidizing velocity for a bed of similar particle, assuming Stokes law and the Karman-Kozny equation are applicable. So the derived the relationship for ratio of the terminal falling velocity of the particle to the minimum fluidizing velocity. Okay. What is the value of ratio if the bed voltage at the minimum fluidization velocity is 0.35? So how you are going to derive it? That is the question. And then you are asked to calculate the ratio u operating to the u minimum falling velocity. So ratio of the terminal falling velocity to of the particle to the minimum fluidization velocity for a bed is similar particle assuming Stokes law valid. So this type of question we have already solved one question. So this question and the question number 2, I think. No, the question number 2, question number 3 was similar. Like here also ratio of the terminal settling velocity to the minimum fluidization velocity has been calculated. When you increase the value number, it decreases. We have told that. Similar question is this one also. So just give some try to this question. So terminal settling velocity is what? When a particle is settling in a fluid under gravity and you are not considering any drag or something. Uh, so that is falling. Obviously, if you consider the drag, those terms will be coming up in terms of CD. So the drag coefficient will come up. But how you will be solving? Um, let's give it a try. So here data is given. So you are given with the value of void voltage which is 0.35 and this is given and you are also given assume Stokes law valid Stokes law validity and also assume carbon cogeny equation. Okay, so just assume this and when you assume it, this will be pretty easy for you, like uh, the the one that we already discussed here, the carbon cogeny equation. Here you see this is the carbon cogeny equation. Okay, so this equation was means you have to consider the laminar situation. So I will be just copying so that we can discuss some more question. Yes, yes. So carbon cogeny equation is this one. Okay, and terminal free settling velocity is u0 equals to d square rho s minus rho g divided by 18 mu. Okay, so this says u0 divided by umf. This was equation 1, this is equation 2. Equation 1 divided by equation 2, divide equation 1 from equation 2, we will get this as d2g rho s minus rho divided by 18 mu into 0.0055 1 minus e divided by epsilon cube mu divided by d square rho s minus rho g. So solving, you will get 1 minus e divided by 80 into 0.0055 into epsilon cube. Solving this, when we put the value of epsilon, 10.1 divided by 1 minus e divided by epsilon cube. And this will come out to be u0 by u minimum fluidization comes out to be 153.12. This is the ratio of terminal settling velocity, the minimum fluidization velocity, which is the option 1 as given in the question. So option 1 is the correct answer for the given problem. Okay, so that's all for this problem. And this is the equation that we came to know. Now we will be discussing some other question. So which of the following statement is correct? Uh, so which of the following statement is correct? Okay, which of the following statement is correct? So question number 11 we are done. I am writing out. Okay. Which of the following statement is correct? Which of the following statement is correct? So the option is particulate fluidization and the aggregative fluidization proceed simultaneously. Particulate fluidization. So let me just take the options. So that time can be saved. The option A is particulate fluidization and the aggregative fluidization. They can proceed simultaneously. Okay, so you just think about this. These are some options about the question. Particulate fluidization and the aggregative fluidization proceed simultaneously. Particulate fluidization is followed by the aggregative fluidization. Aggregative fluidization is followed by the particulate fluidization, and none of the above. So as far as I can explain you this, we have discussed here in one above question. We will be discussing that again. Okay, let it be here. Okay, so this is the situation that is actually taking place. So let's make it big and then keep it here, keep it here. Okay, this will be the another one. So this is the situation. You are increasing the gas velocity, and then these things are happening. So what is the particular fluorization first? When a liquid, the bed continues to expand as the velocity is increased, and it maintains its uniform character with the degree of agitation of the particle increasing progressively. This type of fluid is particular fluidization. But with the gas, it happens. This aggregative Uniform fluidization is frequently obtained only at low velocities. With the gas, only low velocity will give the uniform fluidization. At higher velocities, two separate phases may form. A continuous phase often refers to as the dense or the emulsion phase, and a discontinuous phase known as the lean or the bubble phase. These bubble phases are not desirable in the industries during the fluidization. So the fluidization is then said to be aggregative fluidization. So So fluidization is followed by aggregative fluidization followed by particular fluidization, and which of the following is correct? So if you actually see this this is correct. So this particulate fluidization is particular followed by aggregative fluidization. So after the particulate fluidization, aggregative fluidization will come. So now you understand this particular thing. So this is also clear from the first figure also. Okay. Now let's solve another question. Which is most difficult to fluidize? Which is most difficult to fluidize? The options are, we are solving the 12th question, which is more difficult to fluidize, and like a spherical shaped particle, which is most difficult to fluidize. The spherical shaped particle, the cylindrical shaped particle, the needle shaped particles. Okay, that is the new thing. The needle shaped particle. Which of the following is most difficult to fluidize? The spherical shape particle, cylindrical shape particle, needle shape particle. Fluidization does not depend on the shape of the particle. Obviously, it depends on the shape of the particle. And these needle shaped particles are very difficult to fluidize, as it has been discussed in the lecture. And the reason being very small sphericity, and that actually deviates it for being getting lifted, and for the adequate drag, action of drag. So this is the option C is correct answer for this. So drag resistance in drag, larger shift in the incipient condition, and improper uh, uniformity in the bed. Okay, so that's all about the question number 12. Let's discuss another question, which is question number 13. And that question says this. Let me just take that question number 13. Yes. And the question number 13 is about maximum bubble size can be achieved in. Maximum bubble size can be achieved in. Where you can achieve maximum bubble size. So the option are here. So you have been told about different powders. So this options are here. Like maximum bubble size can be achieved in. So which powder? Group C powder, Group B powder, Group A powder, none of the above. Mhm. So which of the following is correct? So about different powder you have been taught in last lecture, where entrainment also you have been taught, but along with that you have been explained about the powders, and there you got to know about the same, and we will be actually looking for that. And this I will be actually explaining you complete scenario of all the powders, and then this will be more clear to you. So this is the case. This is the explanation about the powders, different powders that you got to know. This was the last lecture of the week, and Gutenberg's classification of the powder also is the one that has to be taken care. Okay, so from here you see maximum bubble size can be achieved in. So this, yeah, there you are given that the bubbling fluidization as fluidization velocity increases, and this leads to the maximum bubble size, which is the group A. Here you see maximum bubble size, group A. So group A maximum bubble size E120. So group A powder is the correct answer. And here remember this, you have been defined different powders. So first powder was when the fluidized by the air at the ambient condition. Give a reason of the non-bubbling fluidization beginning at the UMF minimum fluidization and followed by the bubbling fluidizing velocity increases. Then the powder gives only bubbling fluidization under ambient condition. Okay, only bubbling fluidization under ambient condition. And then powder is very fine cohesive powder which is incapable of fluidizing in the strict sense. Okay, so this powder very fine cohesive powders, if the powder is very fine and they are cohesive, then they will be incapable of fluidizing. So and the last one is the powder the category D, where large particles that are distinguished by their ability to produce deep spouting beds. So that is another one. So these spouting beds actually often found got if the bed is very deep. Okay, so that's all about this question. Now we are going to solve next question, which is question number 14. That is that is that is question number 14 is which material is suitable for fluidization if you are having which material is suitable for fluidization if you are having which material is more suitable for fluidization, rice, cement, sand, and catalyst, which is more suitable for fluidization? Which of the material is more suitable for fluidization? So as you remember, that was the group A, where that is actually the situation in the catalytic cracker. So the catalyst is the one which is more suitable for fluidization. So catalyst is the correct answer for the one question. And then this here, yes, here. Next question is slugging is undesirable. Do you? Why slugging is not desirable? why slugging is not desirable. And slugging actually happens which type of powder mostly? Slugging actually happens when what is slugging? What is this? Formation of large size bubble due to vibration in the industry. Material does not mix properly. None of them. Which of the following is correct? So yes, slugging leads to the vibration in the industry. So this is the answer because lots of bubbles are getting formed and that is that leads to the vibration as this instrument is a bit these are very large instruments which are placed in the industry. So this is the one problem. Okay, now the next question is fluidization is not used in. So question number 16 is fluidization is not used in. So the options are as follows. The fluidization is not used in. Options are this. The options are this, which is pneumatic transport, hydraulic transport, mixing of the solid, size reduction. So for which it is not used. Hmm. Fluidization is not used for. Fluidization is not used for hydraulic transport, mixing of the pneumatic transport, mixing of the solid. So the fluidization is not used for what? Fluidization is not used for. Fluidization is not used for. Fluidization is not used for size reduction. So size reduction is actually a different thing, and all the three options are correct. Only this size reduction is the one which is not used for by the fluidization. So that is the 16th question, and then the 17th question is Karman-Kozny equation is valid for. So I have already solved one numerical. Again, just for your informative sake, I will be again explaining you the things. This minimum fluidization is actually the situation here. So this is the 17th question. So the minimum fluidization condition is particle starts moving now freely in the way particle start leaving its place. So this question I think I we have solved already. So let us take some other question. Yes, this Kozny carbon one we have to solve. So Kozny carbon equation is valid for laminar turbulent. So as you remember, this we have already told that this is valid for laminar flow situation. And the particulate fluidization occur at low gas velocity, high gas velocity, very high gas velocity, all of the above. So particulate fluidization occurs when the gas velocity is low, gas velocity is high, gas velocity is very high, and all of the above. Which of the following is correct answer? If you remember, the particulate fluidization occurs when we have already discussed about the same here. When the liquid, the bed is, and in the case of gas, if the gas velocity is very low. So you just copy these. again. So which of the following is correct? This is particulate fluidization occur at low gas velocity. Low gas velocity. A. Okay. So what is correct for minimum fluidization velocity, and which of the following is correct for minimum fluidization velocity? Which of the following is correct for minimum fluidization velocity? Greater for the spherical particle, greater for the non-spherical particle. It does not depend on particle shape. Equal for spherical as well as non-spherical particle. Minimum fluidization velocity is greater for non-spherical particles. This has been discussed. Option B is correct answer. Okay, so now with increase in the Galileo number, the ratio of the terminal settling velocity and the minimum fluidization velocity decreases. We have already discussed, and then uh, we will be solving what is which of the following is correct for the no, this is not correct one. Let's see this question. Okay, this question could be attempted. Before that, spouted bed fluidization is more suitable for. So I will be giving you another question, which is 20th. Sorry, spouted bed fluidization. Let me see. I'm online. Yes, I'm online. So spouted bed fluidization is spouted bed fluidization is is most suitable for. So option A is mixing of solid, mixing of solid. Option B is drying of solid. Option C is both A and B, both A and B. And option D is none of the above. And none of the above. So as you remember, this spouted bed, as you remember, the spouted bed so as we have discussed that sluggish is attained by large pressure fluctuation, and so it is generally avoided to large units since it can cause vibration to the plant, and similarly uh, Slugging. So slugging we have already talked. I have told you slugging. Slugging is undesirable vibration. So this is there. Slugging we have already. So in the slugging, I will be actually giving you the reference of the slides so that it becomes this. So this you remember slugging. So slugging is the having this answer. So that's correct. And the one that you was actually were actually looking at is spouted bed. Spouted bed one. This is spouted. Now here we have spouted bed as we have discussed that powder falling in the group D, they behave as a spouted bed. The spouted bed is what? If I tell you this, in the spouted bed, the one channel forms in the middle of the entire bed, and that is the one thing that makes it unique. So the one channel that is forming in the bed, through that the solids are moving up, and gradually when those solids which are being fluidized at the center, around the axial section of the center line, they go up and up, they again fall back towards the wall and gets inner annular region of the fluidized bed, and there this this particular this thing is mostly used for the dehumidifying, like removing the moisture from wheat and rice in the food industry. So that is the one application that you should appreciate and you should remember also. So this what actually happens, this spouting beds represent the ultimate in the channeling in a fluidized bed. Gas enters at the conical base, which with much of it flowing rapidly upward through the central core, and the remainder re percolating through the surrounding solid, which may not be fluidized state. The solid therefore forms a wall for the central spout of the gas, gradually becomes entrained and then disengages from the gas stream in the space above the bed, where the gas velocity falls as the flow area increases from the spout area to the vessel cross section area. So here you see spout bed fertilizers are used as a efficient dryer for the drying seeds such as rice and the wheat from the moisture content as given. So this is the one. From here it goes and comes down this side if it is at the first level. So this is used for the mixing of the solid. This is used for the drying of the solid. So for what it is used? So this is used for the drying of the solid as mentioned over there. So the correct option that you should use is the option B. So 20th question we have done, and I will be giving you some questions, so you go through them, and meanwhile I will be telling you the answer. So I will be pausing a bit. So I will be posting one numerical problem one now, and then let's see how it goes. So this is the question, one numerical problem, and this is our 21st question as far as I remember. This is 21st question. So you solved it while I will be joining, and this question is related to the concept that has been already taught to you. So there is not much difference. This will be a big problem for you. So carefully look at this. This will take around 10 minutes for us to get through the solution, and I will be telling you each everything step by step. So you look at this, and still how much time we are left with? We are left with 20 minutes. So I will be giving 4 minutes, and then we will be discussing the question. Okay. So this question says 2 tons of solid particle. So you are having 2 ton solid particle. The specific gravity of the solid particle you are given with are fluidized using 500 meter cube per hour of the gas having density of this and the viscosity of 0.015 centipoise. Solid particles are cylindrical shaped, having 300 micron height of the and the diameter of 1 by third of the height. Compute the diameter of the fluidizer, minimum fluidization velocity. So you have to design the fluidizer in this question. So just read the question and try to solve it. I will be joining. Yeah, just 2 minutes. Okay, so I hope you have gone through the question and you are trying to solve it. And this uh, numerical. So here the point that has to be noted is that here you are using cylindrical particles. So this is not a spherical particle. So this concept of sphericity should come into the play, and this I will be giving you a quick solution about this for the question. So the data given is that mass flow rate you are given with 200 2000 kg, so 2 tons. Okay, and the gas flow rate is gas flow rate is 500 meter cube per hour. Okay, and then here you are provided with the cylindrical shape having about the particle you are giving with this 300 micron to be the height, and diameter is one third of that. So this L by D equals to 3. Now, density of solid you are given with 1500 kg per meter cube, and density of the fluid you are given with 2.5 kg per meter cube. Okay. So UF is equal to 0.000015 kg per meter second. This is the fluid viscosity, and this fluid viscosity is given over here. You see this 0.centipoise. Okay, and then you are given with the ratio of operating velocity to the minimum fluidization velocity to be 4. So this, you see, this is given. Compute the diameter of the fluidizer. Minimum fluidization velocity is one-fourth of the operating velocity. That last line of the same. So minimum fluidization velocity is minimum fluidization velocity is velocity is one-fourth of the of the minimum fluidization velocity is one-fourth of the minimum fluidization velocity is one-fourth of the operating gas velocity. Operating gas velocity. Okay, so these are the data you are provided with, and you are asked to calculate the diameter of the fluidizer. So let us first determine the minimum fluidization velocity. So let us first determine the minimum fluidization velocity. The volume of each catalyst particle is uh, now the volume of each catalyst particle is the volume of each catalyst particle is maybe equals to pi by 4 d square. Also we know that for sphere. So actually we are trying to compare it with this sphere. So this is pi by 6 dv. So when you equate you equate these two, you will get dv equals to 165 micron. How this came? So this is the volume of the sphere, and this is the volume of the particle. So volume of the particle you are going to equate with the equivalent sphere in order to get the equivalent diameter of the sphere that will be having same volume as that of the particle. So from here dv equals to 3 by 2 d square l. This both you are given with 10 to the power 1 by 3. So you are given with L, you are given with D. When you put, you will get 165 micron. So from here, as this dV is given, and the liquid is the one thing that is the used to fluidized. So used to fluidize. So there will be the Archimedes number will be coming out at the minimum fluidization. That is nothing but the Galileo number. Both are same. This has been explained in the lecture also. in the one of the example while discussion of the liquid fluidization. So Archimedes at the minimum fluidization you can calculate using the dV value that you have calculated using the formula as given, and this comes out to be all the values are known. This is known, this is known, this is known. When you put all the values, you will be getting 733.24, which is the ARM value. Okay, so now, like the one question we have solved, where the Galileo number was coming. So here REMF, Galileo number, the minimum fluidization condition can be calculated using 33.67 square plus 0.0408 ARM minus 67. This gives 0.442. So which is VT less than 1. So 0.1. So that is less than 1 anyway. So this REMF is dV VMF rho f divided by mu f. From here, VMF equals to 0.016 meter per second. So minimum fluidization velocity you have calculated. Now, as you remember, the question started with the cylindrical particle that you have used in order to calculate the minimum fluidization velocity, but the diameter of the fluidizer is still the question that is asked. So from here you can write the one thing also given, that this the condition that the operating velocity and the minimum fluidization velocity ratio is 4. So you can use this to calculate the V operating velocity, which is 4 times the minimum fluidization velocity. This is 0.0643 meter per second. Okay, equals to 231.52 meter per hour. Okay, since the volume flow rate of the gas is, since volumetric flow rate of the gas is 500 meter cube per hour. So as you see, it was given in the question, gas flow rate is 500 meter cube per hour. So the area could be calculated as 500 divided by 231.52. This was meter per hour and this was meter cube per hour. From here you will calculate the diameter of the fluidizer to be this. So pi by r square, pi by 4 d square equals to 2.16. From here, when you calculate d to be d equals to 4 by pi into 2.16, 4 by pi into 2.16 under root. So this is 4 divided by pi into 2.16. So let me take the calculator. 4 divided by 3.14 multiplied by 2.16. You just take the under root of the same. So this is 1.658. Okay, this comes out to be 1.658 or 1.66 meter. This is the required diameter of the fluidizer. Okay, this is the required diameter of fluidizers. So this completes this question. So maybe option 1.6 is what the last is correct answer. D is correct. So this complete this question. Now hope this lecture through this discussion you got to know something, and this will help you in order to solve the weekly assignment. And also one more question that I want to ask from the application section of this fluidizers, fluidized bed and all, and there you came to know that this, let me just see, entrainment was there, no? So this, what is in the entrainment you have been told that fluidized bed surface to be composed of different zones. So so what actually entrainment happen, and what is uh, a transport disengagement height? So this, what is transport disengagement height? You look at this. What is transport disengagement height? This is the important concept from the last lecture that has to be taken care. And then uh, this is for your information I am telling. Okay, so 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 which of the following is correct? This is the multiple selection question, question number 23. So the following is correct. Which of the following is an application of fluidized dyes bed or fluidization? The options are A. A is, it can be used as a solid cooler. So fluidized bed, solid fluidized bed, solid cooler. So this can be used to cool the solid. Option A. This can use to cool the solids. Yes, this is the one thing. Whether it is correct or not, in the chemical, this is used in the chemical process industry, and uh, ease of removal of solid from the reactor. Whether it is correct, is used in chemical process. Bad heat transfer between bed of particle and rising gas. Okay, bad bed of particle and can be used able to maintain uniform isothermal situation even for highly exothermic or endothermic reaction or endothermic reaction. So this could be used. Okay, so that is the one thing that I wanted to say. And this is used in fluidized catalytic cracker, fluidized in petroleum plant, catalytic cracker. Okay, so some other examples that could be like using pharma pharmaceutical products, using coal burning, FGH, this is H, coal burning, and chemical looping. So which of the following is correct? So you look at this, you try to solve. This is the application one. So it is used as a solid cooler, is removal of the solid from the reactor. It is correct. Chemical process, it is being used. No, no, this will be good. This is able to maintain the uniform isothermal heat transfer. This is used in the catalytic cracker form. So all are the correct except the one. So answer. So this, you look at these question. Similar question you must be getting in the exam and again in the weekly assignments. So all these will be available on the website uh, through the drive link. So thank you so much for being here. Let's stop this. Okay. So thank you so much. Thank you.